Based upon the previous discussion, this gives us a way to compute the area of a plane region. Suppose R is defined by a less than or equal to x less than or equal to b, and y is between g1 of x and g2 of x, where g1 and g2 are continuous functions on the closed interval a to b. Then the area of R is going to be given by the iterated integral from, usually we put a to b. Let me just switch that around real quick. The iterated integral from a to b of the integral from g1 of x to g2 of x dy dx. Similarly, if R is defined by y between c and d, where x is between h1 of y and h2 of y, with continuous functions h1, h2 on the closed interval c to d, then the area of R is going to be given by the integral from c to d of h1 of x, h2 of x, dx, dy. In example 3, let's use an iterated integral to find the area of the rectangle below. As we talked about earlier, in order to set up our iterated integral, we would want to try to draw a representative rectangle to help us here to see whether or not the region would be perhaps either vertically or horizontally simple. And in this case, we see that it's going to actually be both. This region, if we look at it, is bounded by two horizontal lines, but it's also, if I draw a horizontal rectangle, it also happens to be bounded by two vertical lines as well. So for this particular problem, we actually have our pick in terms of how we might want to go about setting this one up. What I will do, since we already have the vertical bounds here, let's set it up as follows. So I'm going to use the order dy dx. My outermost bounds are going to be in terms of the x variable, and we know x is bounded from x equals to a to x equals to b. If I look at the y heights, this function will go from a height of y equals to c to y equals to d. So it should look like this. It's the iterated integral from a to b, from c to d of dy dx. Let's integrate with respect to y first. The antiderivative of dy, or just one dy, would be y. We now need to evaluate that from c to d. This will be the definite integral from a to b. If I stick in the upper limit of integration, I get d, subtract, stick in the lower limit of integration, we get c. So this ends up being a constant. We can now integrate this with respect to x. The antiderivative of a constant is just going to be that constant times x. And now this gets evaluated from a to b. We will first stick in the upper limit of integration. And then stick in the lower limit of integration. And just to kind of write this a little more cleanly, let's actually factor out, and we could have done this in the very beginning, let's keep that d minus c out in front, factor it out, and this is what we have. It's d minus c, which represents the width of the rectangle, and then times b minus a, which would represent its length. So just as we know, the area of a rectangle is length times width, and we were able to show that using an iterated integral. Let's take a look at another one. In example 4, we're asked to use an iterated integral to find the area of the region bounded by the graphs of f of x equals sine x and g of x equals cosine x between x equals pi over 4 and x equals 5 pi over 4. It's a good idea. I find it a lot of times very helpful just to draw a rough sketch so we can kind of see the region that we're looking at. So from pi over 4 would be here. 5 pi over 4 would be somewhere to the right. The two functions are equal at pi over 4. The sign would look something like this. Starts at 0, it's going to come up. It's going to come up, then it's going to start to go back down. Be like this. For the cosine curve, you would have the following. So this is sine x. This curve on the bottom is cosine x. And this is the region that we're looking for. So we want to find the area that's between those two graphs. Okay. So in order to figure out, what order of integration we want to use on this, let's insert two different representative rectangles to see what it would look like in terms of a vertical region or a horizontal region. The first thing I'm going to do is let me try to insert or imagine this if I had a horizontal representative rectangle. As that horizontal representative rectangle would move through the region, its left endpoint and its right endpoint are going to change. For example, here, the right endpoint and the left endpoint would be on the same curve. When I drop down a little bit, the right endpoint and left endpoint would be on one curve and then the other curve. And then as I drop down even lower, then it would be on the same curve again. So because of that, using horizontal representative rectangles here is not going to make this a very convenient thing to do. However, if I look at what would happen for a vertical representative rectangle, the x's go from x equals pi over 4 to x equals 5 pi over 4, and the top part, the upper bound for the region, for that top part of my rectangle, it's always given by the sine of x, and the bottom part of it is always given by the cosine of x. So this would actually represent a region that would be vertically simple. So let's go ahead and set it up as a vertical integral. So we're going to be using the order dy dx. So let's start with the outermost bounds first. As this rectangle moves through the region, x is bounded between pi over 4 and 5 pi over 4. If we look at the y values, so the y values in this region are bounded between a lower bound of cosine of x and a upper bound of sine x. It's a good idea, especially as you're first learning this, just to check it out. This iterated integral should be fine. The first integration takes place with respect to y, and sure enough, we only have functions of x for the bounds in that first integral, so we should be good to go. Everything looks good. This is going to be the integral from pi over 4 to 5 pi over 4 of y, and that needs to be evaluated from the cosine of x to the sine of x dx. If I substitute that in, I have the integral from pi over 4 to 5 pi over 4. Evaluate the y at the upper bound, that gives us sine x. Evaluate it at the lower bound, subtract, we would get cosine of x. So we now have to find the antiderivative of sine x minus cosine of x. The antiderivative of sine is negative cosine x. The antiderivative of cosine is sine. So this is going to give us negative cosine x minus sine x, and this has to be evaluated from pi over 4 to 5 pi over 4. We would insert the upper limit of integration. It's the cosine of 5 pi over 4 minus the sine of 5 pi over 4. Subtract the negative cosine pi over 4 minus the sine of pi over 4. Let's see if we can kind of go ahead and work those out. The cosine of 5 pi over 4, 5 pi over 4, that's in quadrant 3. So that's going to be a negative square root of 2 over 2. And then we have the negative sign out in front. For the sine, we again get a negative square root of 2 over 2. Minus over here, the cosine of pi over 4 is square root of 2 over 2. The sine of pi over 4 is also square root of 2 over 2. This is going to give us a positive square root of 2 over 2 plus square root of 2 over 2 If I distribute the negative sign in, I'm going to get another plus square root of 2 over 2 plus square root of 2 over 2, which gives us 4 square roots of 2 over 2, which is going to be 2 square roots of 2. So the area of this region, if we were to come back to the original drawing, the area of that region would have an area of 2 square root of 2 square units.